Okay, so the next block is on compaction-induced earth pressure. So if we're doing any kind of a built wall, we're quite often going to be compacting behind it. And there's two reasons you'd want to know the compaction earth pressure. One is, in some cases, you may actually lock in. Obviously, if you're compacting the soil, this is not necessarily an active condition or a passive condition, and it's certainly not a K-naught condition. So when we start running equipment and behind the wall and start compacting it, we're obviously changing the conditions, the assumptions that we had for the K-naught condition, so it can't be that. And we may or may not be at active or passive earth pressure. Those will be limits on what we can have. Those are limits. So there's two reasons you might want to do it. One, you could induce some horizontal earth pressures that you need to deal with for the long-term design. And another reason you might want to worry about it is you probably don't want to break your wall while you're building it. So those are two reasons that you would need to be concerned about compaction induced earth pressures. So I've given you two papers to read on this that go through the theory about what are the compaction-induced earth pressures, and one of which has some really good empirical data for you to work with and some design charts. So one of the learning objectives is for you to be able to understand, to explain when K-naught conditions exist and when they don't. We're also going to essentially start covering walls, non-moving walls. And then you need to be able to explain why the limits on the compaction-induced earth pressure you might get correspond to either the passive case or the at-rest case, and we'll walk through that. And then Peck and Mesri did a really nice paper in '87 that explains how you can get a simplified distribution using Boussinesq theory. And then Duncan, the other paper I gave you to read, which is Duncan et al. And the sort of bottom line to either the Peck and Mesri method or the Duncan et al. Method are both probably equally valid methods for computing lateral earth pressures due to compaction loads, and so you should be able to use either one of those and decide which one you want to use. All right, so let's talk about earth pressures behind rigid walls now, and by rigid I mean non-moving. Okay, I don't mean rigid as in a concrete wall, I mean as in non-moving. So generally, we've always assumed that to date, that the wall's allowed to deflect, and when it deflects, it's going to reach a limit. The minimum limit, because the soil's going to fail behind it, it's going to reach a limit, and you're going to get to the active earth pressure conditions. And as long as the wall is allowed to move, and the movement is quite small, I don't think we talked about displacements to get to the movement. We'll talk about that in the next lesson. But the movement's quite small. But if the wall can't move, then there's no guarantee that you're going to get to that lower limit and get to that low equilibrium limit. And K-naught's higher than K-active, right? So if the wall can't move, you're going to have, you can't get to the active state. The lateral earth pressure will be something greater than the active earth pressure. Now the highest it could be is the passive earth pressure. And there are some cases where people recommend designing the passive earth pressures, by the way. I've seen some design recommendations from Australia for places where there's expansive soils that are highly expansive, and if you can't mitigate them, they actually recommend in some cases design for the passive earth pressure, which is pretty large. Remember KP is like the inverse of Ka. If Ka is around a third, Kp is like 3. So that's a big number. So generally, if the wall is not moving, we're going to assume, in general, it's appropriate to assume that you have at-rest conditions and use K-naught for your design earth pressure. And we'll summarize, one of the things we're going to do next lesson is we're going to go summarize all the theories we have and talk about what approaches you should take for design. So when do we have what's the most common case we have where we have walls that don't move? Basement walls, right? Very common. So if you have basement walls, you got a floor joist, this is going to be your floor. It's going to be supporting this. Another case where that is likely to happen, whoops, is if you've got a box culvert. Lots of times you'll see these box culverts. You better not design a box culvert for the active earth pressure because this is not moving. All right, that's a rigid structure, and you need to design for earth pressures that are rigid. Now, in addition to having this problem, if you start going back there and compacting, you're going to see in a minute that if we have flexible walls, once we compact, the wall just moves more, and we may increase the earth pressure some, but there's a limit to what we can increase them to. But if you've got a rigid wall and you compact the crapola of the soil behind the wall, you could get as high as, what's the upper limit you could get to? The passive earth pressure. And that's a big number, right? You go from 1/3 to 6, that's a lot. So we need to understand compaction earth pressures as one. Sometimes we will be dealing with things like braced walls or box culverts or something where we do really need to be able to estimate what the compaction earth pressures are and deal with them. And in other cases, we want to do this because we want to avoid it. But we need to know in either way. So let's talk about what's going on when we do compaction. So if we have a rigid wall here, so we have a non-moving wall. By rigid, in this one I probably should have said non-moving, but I mean non-moving. So so this little exercise I'm going to show you only applies to rigid walls, but we'll talk about what happens to flexible walls. So in general, we use lightweight compaction behind the walls because we don't want to get to passive. We don't want to break the walls. Okay, so here's your common compaction process. You place a layer of soil, right? And then you're going to run some kind of a compactor behind it. And it's almost always, even if it's not a vibrating compactor, it's going to be cyclic compaction. In other words, that compactor is going to move up and down behind the wall. So a load is going to be applied and taken off, and applied and taken off, and applied and taken off. And it may be a dynamic load, but even if you're using a static compactor, it's not like one pass and you're done, right? It's going to take several passes. So it's going to be a cyclic line load if you want to think about it. Right, you're going to put a line load on, you're going to let it go. You're going to put a line load on, you're going to, Okay. Then we're going to put a new layer on, and we're going to do the same thing. So the sequence is really important to understanding the process. So we just keep doing this until we get to the top, right? So there's two parts of the process that are important to understand. One is we increase the total vertical stress with the surcharge, and then we put an additional vertical cyclic load on it. So it goes on and off, on it. It's a cyclic load, on and off, on and off, on and off. And then we're going to and then that same spot's going to get loaded again up to a higher stress, and then above it there's going to be a load applied and off and off and on. Okay? Those two pieces of the process are important to understanding this. So what's going on here? Well, here's our initial surcharge placement of the fill. So this is sigma z and this is sigma x, right? So z is the surcharge fill. Well, it's going to be two sigma x's. It's two sigma z's. One's going to be a surcharge fill and one's going to be my dynamic load. And then I'm plotting the horizontal stress that's going to be generated from that. So if you're just placing a fill, you're going to have a fairly low earth pressure coefficient, and you're going to get more vertical stress than horizontal stress, right? And then it should be going up the K0 line if it's at rest. Now, if it's loose, it might be less than K0 for the final version, but at least theoretically, in the first order, we're going to be traveling on our initial loading, we'll be traveling up the K0 line, because that's the definition of at-rest earth pressure, right? Highest load the soil's ever seen. Right? Well, then we're going to put our compaction load on. And if this is our first lift, the vertical stress is going to be very, very small, and we're going to put a big-ass compaction load on it, right? Well, that's the first pass. Now, what happens when what path are we going to follow now when the compaction device moves on past this point? So we got one load on and we move past. Well, think back to our K0 1D compression lab data that we saw. So once the compactor leaves, we know that sigma. So we're at this sigma z, we know we're going to come back down to this sigma z here, right? We're going to go from, this is sigma z for the fill level, right? That we're at. I'll have to call that 1 because it's going to go up. This is the dynamic load. So we know that our stress is going to. So are we going to go this way? Are we going to go this way? We're going to go back down the K naught line. What's going to happen? We're going to go above or below the K naught line. You've actually already seen this figure. So it's either going to, there's only 3 things it can do. It can go back down the K naught line, or it can go above the K naught line, or it can go below the K naught line. Which one's it going to do? So I've applied a stress, and I'm going to unload. Is my horizontal stress going to go back down to the same level that it was before I loaded, or is it going to be higher than what it was before I put the load on? Am I going to lock in horizontal stresses, or am I not locking horizontal stresses? Think. I feel like you're all dead. All right. I'm going to load it. What happens to K? What's K for over-consolidated soils? Is it higher or less than K for normally consolidated soils? Higher. Thank you. I don't know if you guys are just bored or like you're like tired or like you're stupid. I don't think you're stupid. K naught is equal to 1 minus sine phi. This is our estimate of it, right? What's the other piece of it? OCR raised to the sine phi. So as the overconsolidation ratio goes up, what happens to the K naught? Goes up. So which way am I going? Above the line? Below the line? We know we're not going down the line. We just said that. Above the line. So this is my first unloading. So I passed over, my rollers passed by once. How far can I go down that way? Well, it can't go past the passive line, right? That's the other failure surface. So no matter how much it unloads, I can't get below the passive line, right? And I still have to get, I haven't gotten down to this stress yet. So now I'm going to go down the passive line until I get back to the original stress that I was at. Okay, everybody with me so far? Yeah? Tran, you with me? Yeah? No? Okay. So now what happens? Yeah, the roller comes back by again, right? And what's going to happen this time? Well, now I'm going to load up kind of parallel to the K naught line, but I'm going to be stiffer than the K naught line. And then I'm going to go back down, and I'm going to go back up. And these might go, depending on where the roller, this reloading could come all the way back up to this stress, or it could be, as the roller gets farther and farther away from the wall, it'll be smaller and smaller. But I'm going to have this little cyclic loading thing going on. There's kind of like a hysteresis loop going on there, right? Looks a lot like a hysteresis loop. And then finally, I'm going to put a new lift of soil on, right? And I've conveniently made that the same as the dynamic stress. But this is going to be sigma fill 2, or maybe it's sigma fill 5. Doesn't matter. But sometime after that, some lifts higher, I'm going to have a stress, right? And now when I load this time, I'm going to go above. I'm going to be loading up the, when I apply my dynamic load now, I'm going to be loading up onto the K naught curve. Whoops, excuse me, back up. So the stresses that I'm going to get induced have to lie between the K0 line and the KP line. And they're going to get closer to the K0 line as I at the bottom of at the base of the wall, right? I'm going to have at the base of the wall, I'm going to have K0 conditions because I'm going to put a little bit of soil and compact it, and then I'm going to have a whole much more soil. My dynamic compaction might only been to this point, but by the time I put all the other lifts up, I'm going to be up here. I'm going to be on the K0 line, right? But what about near the ground surface? Near the ground surface, I'm going to be someplace in here because the highest load it's going to seem is going to actually have been the dynamic load from the compaction device. So near the ground surface, I'm going to be above K0 conditions. But I can never get higher than passive conditions. That part you got to understand. Questions? Do you understand that? At the base, you're going to have K0 conditions, and near the surface, you're going to have something higher than K0 conditions, but they won't be as high as passive. All right. So my vertical stress profile then, it's got to be limited between K0 and K passive. So if this was my roller load and I just applied it at the surface, this might be my Boussinesq stress distribution that I would get. Right? Just from the equations we just went through, right? I've got a line load perpendicular to the wall, finite width line load perpendicular to the wall. I can go through that. I just closed that file. I can go through that equation. I can calculate the vertical stress as a function of depth, and this is the figure I'm going to get. Well, some of that can't exist, right? Obviously, I can't have anything that is above the KP, and because of the dynamic loading, it's not going to be less than K0. And I can go through a little exercise, and Mesri does this. Mesri and Peck and Mesri do this for you to show what the theoretical distribution of stress. This is kind of assuming you have infinitely thin layers, and you just keep building it up and up and up. So down low, again, at some point down low, I'm going to be at K0 conditions because all the layers that I put above that have basically eliminated the soil's knowledge of the dynamic load it have, and it's back onto K0 conditions. Where near the ground surface, the last thing the soil remembers is some guy with a big roller pounding on his head, and that's what he remembers, and the stresses are going to be closer to the K passive because that's the limit of the stress you can induce from the roller. And in between, you're going to get a curved solution, and you got to read Peck and Mesri to understand why it's that way. And there's the equation for it. Isn't that nice? So you need to be able to qualitatively describe why this curve looks like that. And this part of the curve and this part of the curve should be simple to understand. And the part in between is in between. Okay? Questions so far? Okay, so let's talk about some solutions for it. So this is Peck and Mesri's solution for it. It's an approximate solution, but their suggestion was, this is nice, it's fancy, it's just theoretical anyway, so why don't we just use this as our stress distribution? And so it's nice, it's simple, it's relatively easy to calculate. They'll explain when you read the paper, they'll explain the details of how they get to that solution. So it's a pretty simple one. It's also a nice, easy one. The other thing I like about it, it's an easy one you can put in a spreadsheet. It's easy to code up. And it should work pretty well for you. Notice all this time I'm talking about rigid walls. If the wall's allowed to move, we'll talk about this before we finish. This is not going to happen. If the wall's allowed to move, we're almost always going to get to the active condition. So what's important is we said design walls. We design things like basement walls to K-naught conditions. If you have significant compaction behind them, it's going to be higher than K-naught conditions, right? This is your K-naught line right here, right? This is K-naught, or this is gamma Z. Or the other way around, I guess, sorry. This is K-naught, and this is gamma Z. All right, so here's here's their equation. By the way, here's another equation you can use for Poisson's ratio if you want to. The only issue with this one is you've got to know the compaction mass, but that's there's a pretty limited range of compaction devices that are used based on the type of construction you're doing. The other thing that's nice about this is you can go in there and put in, you can calculate the loads, decide what you want to limit them to, and then go write specifications for the maximum mass of compactor behind there. If you're worried about it and you want to keep the stresses low, you could go in there and figure out, well, what kind of compaction device can you use. And if you see, has anybody seen a wall compacted recently with these remote-controlled compactors? And they're small, right? About the size of this desk. Yeah, the last time I saw a wall constructed, the guy was out there, 30 feet from the wall with his little joysticks, driving the little compaction device back and forth behind the wall, and things no bigger than this desk. That's a really nice solution. You used to see a lot of people using pan vibrators to compact behind walls because the vibration gives a real nice density without a lot of stress. But now I think I've seen this more. Well, I don't know if I've seen it more often. Was it pretty common from what you've seen? Yeah, the thing's about the size of a golf cart, and the guy just sits there. You know how the guys with the pump with the concrete pumps now, they don't have to stand near the truck. They just sit there and they can stand right where it's placed and see what's going on. It's the same sort of thing. It's pretty cool. I got some pictures of that someplace. I didn't think to bring them in. Oh well. So another nice thing I like about this is you can go through there and say, if somebody's concerned about it, and somebody comes to you and say, well, how big a piece of compaction equipment can I put behind there? And you can say, well, I don't want the loads to be higher than this. You can go back there in half an hour. You could have a calculation. Say, well, don't use anything higher than 20 tons or something like that. So, Duncan, which is the second paper that's assigned for this. So Duncan has a lot of nice design charts. And what I like about Duncan's stuff is it's a combination of empiricism and theoretics. Yeah, you don't have this. You're going to have to draw. No, I'll post the copies of this. Besides, you're going to read the paper, and then you won't need it anyway, right? Smiling at me. Okay. What I like about Duncan's charts, now notice that Duncan's charts are they look, here's K-naught. These are the K-naught lines for various unit weights, see? And so here's the K-naught lines for various units weights. And then these are the compaction lines for different roller masses. And he's got separate ones for compaction by rollers, compaction due to vibratory plates. And what do you notice a big difference between the vibratory plates and the rollers? What's the big difference between those lines? Horizontal scales, same or different? Can you read it? Can you even read it? This is 1500, that's 1500. Vertical scale, that's 28, this is 28. These lines are the same. So what's the big difference between small vibratory pan rollers and big compaction rollers? Lot more locked in lateral stress for the big rollers, right? Yeah. That's why you see a lot of guys using the vibratory pan rollers. So what's nice about Duncan's charts is, first of all, they're nice charts to use because you can go direct to them. You don't have to. You don't really have to you don't have to go there and calculate the mass of the roller and all that kind of stuff. Bad thing about them is you can't program them in a spreadsheet or anything like that. You're gonna have to go through and use them graphically. And there's empiricism. He's also got some. It's not just theoretical. It's got empiricism. But notice that these curves all have the same shape, right? You got loads above K0, and then it comes down and hits the K0 line wherever it hits the K0 line. And he's just plotted different K0 lines based on the density of the compaction density. And then this one is due to ram plates, you know, the little hopper ones. What are those? You know the ones I'm talking about, the ones that bounce around? They look like a pogo stick with a gasoline engine on the top of it. You know what I'm talking about? I forgot what they call this. Huh? Yeah. Boom, 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 boom. Yeah. And then he's got adjustment factors based on lift thickness, distance from the wall, lift thickness, sorry, those two, and roller width and friction angle. So it's a nice comprehensive thing. It's fairly fast, but it's a chart solution, so it's not something you could automate in a spreadsheet or something like that. So I think these two solutions together give you a nice set of tools. One's got a nice analytical form. It's kind of a pain, it's a kind of a big equation, but once you get it programmed, it's not a big deal. And you can calculate analytically what you want, and you could do, you could do nice trade-offs, but it's theoretical. It's not empirical, so it doesn't, which is good and bad, right? And you've got to put in the information about the device. And these ones are easy to look up and get the distribution, but it's a little harder to do what-ifs from, and you can't automate it and program it. So, but those are two nice tools to have in your toolbox. And I think, I don't remember, I think the FHWA manual uses the Duncan charts, but I can't remember offhand right now.